Welcome to the Explainer. Today, we're tackling a force you feel every single day, but you probably don't think about it all that much. It's what keeps your feet on the ground when you walk, and it's what creates that incredible fiery spectacle when a spaceship comes back to Earth.
Okay, so let's start with a really simple question. Picture this. You're trying to push a big, heavy box. Now, on a smooth, polished kitchen floor, it's tough, sure, but you can get it going. But then you take that exact same box outside onto some rough concrete, and suddenly it feels like it's glued to the ground. Why is that? It's the same box, right? Same you? What's different?
To get to the bottom of that, we have to look at what's happening behind the scenes. Our investigation starts right here with what we're calling the unseen slowdown. And you know, it's not just about pushing boxes around. Think about it. You roll a ball across the lawn. It doesn't keep going forever, does it? Nope. It slows down and eventually stops. Or when you're on your bike and you hit the brakes, you come to a halt. In every single one of these examples, there's some kind of invisible force working against you, always trying to stop the movement. It turns out, it's the same invisible force in all these cases. So it's about time we put a name to our suspect and figure out what's really going on. What is this force that's always pushing back? And here we have it. The force is called friction. At its heart, it's just the force that fights against motion whenever two surfaces touch each other. That's it. It's the simple reason the box was so much harder to push on the rough ground. That surface was creating way more of this opposing force. You know, friction has a bit of a personality. It's always contrary. If you push a book to the right, friction pushes back to the left. If you pull something towards you, friction is pulling away from you. It always works in the exact opposite direction of whatever you're trying to do. It's kind of like the universe's own built-in brake pedal.
Okay, so we know what friction is, and we know it happens when surfaces touch. But the really cool part is why? Why does it even happen in the first place? To see that, we've got to zoom in. I mean, way in.
Just take a look around you right now. The surface of your table, your phone screen, maybe a window. To our eyes, they look perfectly smooth, right? Almost like glass. You'd think sliding something across them would be totally effortless. So here's a question for you. What if we could take one of those perfectly smooth surfaces and put it under an incredibly powerful microscope? Do you think we'd see that same flawless landscape?
Well, the answer is a huge no. The hidden reality is that on a microscopic level, no surface is actually smooth. They all have this rugged landscape of tiny hills and valleys. So when you put two surfaces on top of each other, their little bumps and grooves get caught on each other. They interlock. That interlocking is the real source of friction. It's basically a microscopic traffic jam that resists any attempt to move. So if every surface has these little bumps, does that mean all friction is the same? Oh, not at all. Not even close. This force has a bunch of different faces, and it can act totally differently depending on the surfaces involved.
A really simple experiment shows this perfectly. If you take a brick and pull it, you need a certain amount of force. If you wrap it in a smooth plastic sheet, it's about the same, pretty low. But wrap that same brick in a piece of rough jute cloth, and suddenly the force you need to pull it jumps way up. Why? Well, the rougher jute surface has much bigger hills and valleys, so they interlock more strongly. More interlocking means more friction. Simple as that.
Let's go back to our heavy box again, and let's ask a question that I think we all instinctively know the answer to. What takes more effort? That initial big shove to get the box to even budge? Or the continuous push you need to keep it sliding across the floor? The answer to that question actually reveals that there are two different types of friction. That first big push, that's your battle against something called static friction. It's the force that keeps things locked in place when they're still, and it's always the biggest hurdle to overcome because those microscopic hills and valleys have had time to really settle in and lock together. But once you've won that battle and the box is sliding, you're dealing with sliding friction. It's still there pushing back, but since the surfaces are moving, they can't interlock as deeply. And that's why it's always a little easier to keep something moving than it is to get it started.
Okay, so friction is always resisting us, slowing things down, wearing things out. You might be starting to think that friction is the bad guy in this story. But is it really a foe, or could it actually be a hero we can't live without?
Let's look at the evidence for friction being our friend. The grip between your shoes and the floor, that's friction. It's the only reason you can walk or run without just slipping and falling over. Being able to write with a pen or on a chalkboard, yep, that's friction too. It's what holds nails and wood and screws in the wall. It's even the spark that lights a match. Honestly, our world would be an impossibly slippery mess without it.
But there is, of course, a flip side. Friction is absolutely a foe.
It's what wears out the soles of your shoes and the tires on your car. In any machine with moving parts, friction is constantly wasting useful energy by turning it into unwanted heat. Go ahead, try it. Rub your hands together really fast. Feel that warmth? That's friction in action. And over time, that constant rubbing causes wear and tear that just breaks things down.
And all of this brings us to what might just be the perfect way to describe it. Friction is a necessary evil. We absolutely, positively cannot live without it, but at the same time, engineers spend their whole lives trying to find clever ways to reduce it. It's this fundamental trade-off that's just built right into the physics of our universe. So I'll leave you with a final thought to take with you. Now that you know what it is, how it works on that tiny microscopic level, and its double life as both a friend and a foe, the question is, where will you spot friction in action today? I promise, once you start looking for it, from the way your fingers grip your phone to the brakes on a bus, you'll realize this unseen slowdown is absolutely everywhere, quietly shaping every single moment of your day.